I know how much you guys love your triangles, but we are going to step away from triangles for a little bit. Now, you will still see them. They'll still appear, and they're going to appear in this lesson, but the main gist of this entire unit is going to be circles. So the first part about circle, we want to be able to name segments, understand what their segments are, and then understand their relationships in a circle. Don't take this little lesson for granted. Make sure you understand what everything's called, because I'm going to use it going forward, and you're going to need to know what everything's called so we can refer back to it. So, most of you guys have seen a circle, but it's a couple of vocab things that we need to go over. First of all, a circle is a set of all points equidistant from a point called the center. Okay, so that center is the same distance away from all the edges, if you will. A circle is named by its center. So we could name a circle as circle R or Q or whatever it is. The one to the right here below is circle I. A circle divides a coordinate plane into three parts. You could be on the circle. You could be on the circle, the inside, or the outside. Can't write today. Okay, so those are the three parts of the circle. On it, in it, outside of it. And we'll get into that as we go. A couple more things. A chord is a segment whose endpoints lie on the circle. For example, DL is a chord. TO is a chord. Okay, those endpoints lie on the circle. DT is a chord. Okay, so we have three right there. Anywhere you see those endpoints on the circle. A diameter is a special kind of chord. It's one that goes right through the center of the circle. And in this case, we only have one diameter, that is DL. Something else you might have heard of radius and diameter. A radius is half the diameter of the circle. So for example, we could say EI is a diameter. We could say DI is a diameter. We could say IL is a diameter. Okay, so we have all those. I don't know why I just changed the way I wrote an I on that last one. But again, all three of those are radii. Next one. A line that intersects the circle at 2 points, meaning it goes through at two different times, is called a secant. And this is where secant and chord are a little bit similar. Okay, it's really just about how you label things. So for example, if we want to say DT is a secant, we have to make sure we say it's line DT because it passes through. If you cover it up after where DT passes through the circle, it looks like it's just a chord. So you got to be really, really careful. And that is the only secant on here. So it's something that passes all the way through. Last one is a tangent, and that is a line that touches the circle at exactly 1 point. So the only one we have here would be LZ. And that's a line. Okay, so you have all your vocab. Again, make sure, quiz yourself if you need to, which one's which. But those we're gonna use going forward. A couple other things about circles. Two circles are congruent if and only if they have congruent radii, meaning if one circle has a radii of 3 and another one has a radii of 3, then they're going to be congruent. Pretty self-explanatory, because if you spun that radii around everywhere, it would be 3 here, and then 3 here, so everywhere it's 3, so it's equidistant. Concentric, meaning share, co-workers share something. Concentric circles are some circles who share a center. Two coplanar circles that intersect at exactly 1 point are called tangent circles. So that goes back to what we set up here, where LZ was a tangent. So tangent really means it's touching at 1 point. So tangent circles touch at 1 point. It could be inside or outside. First tangent theorem we're going to look at. A line is tangent to a circle if and only if it is perpendicular to a radii, or radius I should say, of that circle. Meaning, the picture I have on the left there, AB is perpendicular to LB, which means there is a right angle. Keep in mind, this radius could be anywhere. You could have another tangent line down here, and they intersect at that point. okay? And they would make a right angle. So anywhere you see a radius and a tangent line, they're going to make a right angle. What this means is, and this is where we get to go back to our triangles, we'll be able to form a right angle here, or a right triangle, and use your favorite Pythagorean theorem. And hopefully by now you guys are able to say that little tongue-twisting name. Okay, so again, that makes a right angle, and we're going to use that here in a second to find some information. So given z, solve for x. Okay, keep in mind, x is a radius. You can use that radius here, here, or where it's going to help us the most, right there. So we have three sides. We know this is a tangent line, so it makes a right angle. So you guys know the drill. X squared plus 24 squared equals, be very careful here, this is where you have x plus 16 squared. Okay, because it's x plus that 16. So be careful on that. So we have x squared plus 24 squared, I believe is 576. No. Yes, it is. 576 equals, you got to FOIL that one, so really get rid of that 2 and make it x plus 16. Otherwise you might forget to use your middle term. So x squared plus 16x plus 16x, we're FOILing, plus 16 times 16 is 256. Okay, now you might be thinking, oh, I'm going to have to factor all that, it's going to be a mess. Not always. What happens here is if we subtract one x squared from the other x squared, they cancel. So we're actually in pretty good shape here. So we're left with 576 equals 32x plus 256. Subtract 576 minus 256, and we get 320, and you can see that 32 goes into 320 10 times. So there is your x. You could check it, you could plug it back in, and double check your Pythagorean theorem. Number 2. If we look at number 2, again, we know this radius can be used everywhere. So we know if we draw this in, that's 6, that makes a right angle. Now, I want to show you a different way to do number 2 because you have this option available. If you don't like dealing with factoring, what you could actually do is something like this. And you could find c. And you could say, okay, 6 squared plus 8 squared equals c squared. 36 plus 64 equals c squared. 100 equals c squared. So the square root, c is 10. Now, this is where you have to be really careful. That doesn't mean x is 10. That means c is 10. So if c is 10, part of it's 6, that x is going to be 4. So if you do choose to do that way, instead of doing 6 squared plus 8 squared equals x plus 6 squared, you just have to be really careful. And again, you're only going to get that option sometimes. Like, we could not have done that in number 1. It wouldn't have worked because we have an x in 2 spots. Okay. Moving right along. In number 3, again, you see those tangent lines. Anytime you see that, you know there's going to be right angles right here. So we already know that's 90 degrees. Here's 90 degrees. It's a four-sided figure. Some of the interior, you guys already know by now that there's 360 degrees in a four-sided figure. You should know that. So we're going to have two 90s plus a 33 plus x, let's go ahead and find it, equals 360. So we have 180 plus 33 plus x equals 360. So 180 plus 33, and we're going to get 213 plus x equals 360. X is going to end up being, what is that, 147 degrees. And again, it kind of makes sense because it's an obtuse angle there, but x does come out to 147. So again, basic idea here is that your tangent is going to make a right angle with that circle, or with the radii in the circle. Your second tangent theorem, and this is all we're going to really cover today, if two tangents are drawn from the same point outside the circle, so if they were both drawn from here, the segments are congruent, which makes sense because if they're drawn from the same point, they're traveling the same distance, so these are congruent to each other. Using theorem 1, we can also conclude that the two triangles formed are right triangles, and I'll show you how that happens here. So if we were, again, to connect this to our radius, right angle, here's a triangle working down the middle. Okay. So again, we might use that going forward, but the main idea is, again, it makes a 90-degree angle, and they are congruent to each other if they're drawn from the same point. So, got my little smiley face guy. We want to solve for the variables, so this will be pretty quick. Two tangent lines drawn from the same point, they're congruent. You guys know the drill, we've been doing this forever. Set them equal to each other. And let's go ahead and get everything on one side. So we're going to add 3x over, subtract 12 over. So we get x squared plus 4x. And then we had minus 12 equals 0. Kind of doing that in one step there. We need to figure out what two numbers work. And we need a plus. We need a minus because we have a negative product. So you guys are experts at this by now. That would require us to have 6, negative 2. X plus 6 equals 0. X minus 2 equals 0. So x equals negative 6. X equals 2. You check both. You always, always, always check both. The positive is usually the easier one to check and is usually correct. So 2 squared is 4. 4 plus 2 is 6. 12 minus 6 is 6. So that one works. X equals negative 6. Negative 6 times negative 6, or negative 6 squared in parentheses, is 36. 36 minus 6 would be 30. And the other one, 12 minus 3x. So we're plugging in a negative 6. Negative 3 times negative 6 is 18. 18 plus 12 is 30. They both work. Always check both. You guys are probably sick of me saying it by now, but it keeps happening where you guys don't check. So double check both. Last one, two tangents. Again, same idea. A little fraction mixed in there. I'll show you how to handle that. Okay, a couple of different things you can do. If you want to, you could put your left side over 1. You could also multiply the right side by 4. I'll go ahead and put it over 1 because you guys are pretty used to cross multiplying. So you have 4 times 3x minus 55 equals x. 12x minus, let's see, that comes out to 220. Yep, equals x. And let's go ahead and move that 12x to the right side. Negative 220 equals negative 11x. 220 divided by 11 is going to give you, I believe, 24x. So if you plugged it back in, you would get a 5 and a 5. 20 divided by 4 is 5. 3x minus, or 3 times 20 minus 55 is going to give you 5. And the last one, a little bit trickier. In our last one, you have, these kind of look like ice cream cones, or a face if you have that behind there. In the last one, you have two circles, and you have tangents to both of them. In other words, this is congruent, and then so is this. That distance from there to there. Those are both going to be congruent. So the first thing we can say is actually really simple. X equals 41. Those are equal to each other. So there's x. Easy enough. Now to find y, all we're going to do, plug in 41. 41 minus 32 equals 9. So if we know y is in the same spot, well, y is going to have to be equal to the same thing, so y is going to be 9. So it looks a little bit tougher, but really, it's all about tangents. You know they're congruent here. Before we had a couple problems where they were perpendicular, made 90-degree angles, but that's really the focus of the first day, along with making sure you guys know your vocab from the top. We're going to end up doing the group work tomorrow, so you can take a look at it. You can work ahead, as always, if you would like to, and then you're an expert in your group. I will see you guys later.